Everyone, in this video we will be discussing about transformers that are being used in substations, in extra high tension substations. Here we'll discuss just a fundamental about the transformer, the different types of transformer, the constructional features, nameplate details, accessories and protections, operational practices, summary. Mostly this video will be helpful for those who knows the basics of electrical engineering and comes in contact with any industry or any kind of institution where they don't have the hands-on practices about the transformer. It will be introductory video for the students who are now in a phase to bloom as a budding engineer. As we know, transformer is a static device that transfers electrical energy from one circuit to another circuit through inductively coupled electrical conductors that operates on the principle of mutual induction. Here you will see two different winding, primary and secondary, and they have a common iron core, and the voltage is being stepped up or stepped down based on the requirement. That is the principle. The theory is the same, and we have the power and frequency constant. The input power and the output power remains constant, but the voltage and current on the primary side and the secondary side is designed based on our requirement. Here you see the cross sectional view. Most of the students who have studied the circuit diagram here and the equivalent circuit diagram, but when they come in field or any industry, when they see such type of transformer that is on the right hand side, they got shocked that where is the winding, where is the core. So all these are enclosed in a chamber, and only we get the output terminals, the primary and secondary terminals, either HB or LV terminals, and that is connected to the bus bar or the circuit we want to get the voltage stepped up or stepped down. And the major part here is for power transformers. The core and the winding are immersed in uh, a EHB grade oil, transformer oil, which acts as both the dielectric as well as cooling purpose. And that plays a major important vital role for field engineers, the transformer oil. Next, we will see the classification, overall classification. So we can have single phase or three phase transformer according to phase sequence. According to design, it can be core type or cell type. Similarly, according to the insulating medium, as I discussed in the last slide, it could be liquid filled or gas filled or dry type. And according to applications, maybe power transformer, auto transformer, interconnecting transformer, distribution transformers, or different types of reactors also. Next comes, here you can see, apart from the core and the winding, these are all other accessories of a power transformer. The insulating material, the transformer oil, the tap changer. Why we need a tap changer is sometimes the primary side voltage may not be constant, and we should maintain the secondary voltage to a certain level, because the equipments which are connected on the secondary, their rating can differ if the primary side supply voltage fluctuation is there. So in order to either control the primary or secondary voltage, there are tap changes in the winding, and accordingly we can get a regulated output voltage apart from the variation in the primary voltage. And the oil conservator, what happens is, as I said, in the body main tank we have the core and winding, and the insulating oil also plays in a part in cooling the heated winding. And when it is getting heated, the oil circulates through the conservator tank, it's shown in the picture, and again it is coming down the main tank. And this circulation goes throughout when whenever the transformer is in service. The different types of cooling tubes are there, radiator is there, and glucose relay that we'll see in our next videos, and the explosion vent. What are the purpose of these uh, accessories that we'll be seeing in detail in our coming videos. Here you can see a real-time photo of a auto transformer and a power transformer. Here the HBLV bushings, you can see clearly the radiators, the cooling fans, and in some cases cooling pumps are also there. And the supply output terminals, incoming and outgoing terminals, you can see the conductors are connected to the bushings. Next comes to the details of the nameplate. So whatever description here given here, it plays a major important role about uh, when we have to commission a transformer in a substation for different types of operation and maintenance, then for testing. These are the parameters, nameplate details we should know whenever a transformer is in service, or we are going to procure a transformer. Based on our requirement, these are the details will be there in the nameplate. So the make, the company, the serial number, the cooling type, and then rated MVA, rated KV, bidirectional or unidirectional power flow, then ampere on both primary and secondary side, then number of tap positions for the tap changer, and at a normal tap what should be the percentage impedance, insulation level, oil volume, oil mass, total mass, temperature rise, year of manufacturing, and at last when it is being commissioned in a substation, the date of commissioning, make of OLTC. If it is not in of the parent company, then any other company OLTC has been used means that has to be also mentioned, and the type of OLTC. So primarily, I'll say just these five things, that power, rated power. So based on that, we can calculate what is the load handling capacity at different cooling stages. Okay. So for example, 31.5 MVA. That means based on our power factor, what will be the active power that can be transferred from the primary to secondary, and at what percentage we should operate the transformer based on the cooling strategy we are maintaining. Similarly, the vector group, crucial for our phase shifting and parallel operation. And next is the impedance. It also determines what will be the fault current and voltage regulation, the insulation class, and tap changer range. At what uh, percentage it can maintain the system voltage when the incoming voltage changes, and under varying load conditions. Next comes the OLTC. As I said, the primary or the secondary, depending on the type of OLTC, the tappings are being provided, and by varying the tappings, we can get regulated output voltage. Other things related to OLTC we'll be discussing later on. Then comes the cooling. Cooling here, as I said, the transformer oil is being circulated through the radiators to the conservator, and uh, the heat is being radiated through the radiator and excess oil is being transferred from conservator to the main tank. This cycle continues. So in some cases we have oil natural, air natural. That means no extra effort is taken for cooling the oil. Sometimes we use extra fans near the radiator, and that is called ONAF. Then comes oil post, air post, wherein you can see a pump is being used for extra circulations. Next comes oil natural water post and oil post water force. And these are different cooling techniques that are being used at different types of transformer. I mean, the rating may be less, then we can go for ONAN. If it is a ICT or auto transformer, then the heat and energy that has to be cooled and the transformer oil that has to be go for ONWF or OFAF depending on the requirement and the loading capacity. Here you see near the transformer another red color box is there. This is a NIAPS system, that is nitrogen injection fire protection system. As we can see already, we have a electrical circuit and the flammable transformer oil. So to protect the transformer, and it is the costliest device in a substation, so at utmost care is being taken to protect the transformer, because most of the time the transformer service is more than 25 years. If it good care is taken, then it can serve up to 30-35 years also. That's why fire protection is very much essential, and this kind of now devices are being used for in case of any fire explosion takes place, then that can be prevented for further damage. Next comes the transformer. As I said, it is a costliest device, and the protection and care and maintenance has to be taken judiciously. So in case we need a certain power handling capacity transformer in a substation, then additional one separate unit is there, that is the n minus 1 criteria is being fed, because once it is taken out for servicing or for repair or for maintenance, then that time the substation cannot be in blackout. Another transformer has to be there to cater the load. To maximize our reliability, we always go for N minus 1 criteria, and that's why in most of the substations, based on the loading, more than two or three transformers are there, and that are being operated in parallel. And you must have studied the theory that we should have same vector group, same voltage ratio, same frequency, same polarity, same phase rotation for paralleling the transformer. And how the load sharing is being done for two type of transformer, and as we have seen in our nameplate, the percentage impedance. Based on the percentage impedance, we have this formula, and the power is being shared among the transformer. For example, some transformer may be around 12.5 MVA, some may be around 20 MVA, 40 MVA, 60 MVA, 65 MVA, like that, and they can have different impedance that can vary from 9 to 12 ohm, and based on their impedance, load handling capacity, the load parallel operation and load sharing is done. Next, these are the pictures for our digital future. Here, these are coming as new generation technologies, that is digital twins. They're simulating the thermal performance of the transformer to optimize the load. Similarly, another one is we should go for condition based maintenance from time based. Earlier, it was monthly, daily, weekly, and quarterly, half yearly, annually. Those were the guidelines were provided as per standards and from manufacturers and grade code. So based on that, maintenance action was being taken. But now, based on individual health index, the monitoring action and testing should be done, which can enhance the performance of the transformer as well as the substation. Similarly, automated tap adjustment for voltage stability. Earlier, the tap adjustment was done locally and manually, and it was taking a lot of time to get the voltage stabilized. But now, more action is taken for getting this automated tap changing positions for maintaining the grid voltage stable and reliable. So, these are the new techniques emerging in case of transformers, that can be a power transformer or auto transformer or ICT. So these are the standards available for the core, the transformer testing, for protection, for safety, for efficiency, for cooling class installations, and based on these guidelines only, the transformers should be treated. And as we know, transformer is the backbone of a substation. Proper monitoring prevents major failures, and the importance of oil quality and cooling system are very much critical for maintaining the system health normal. Then we have different protection system which provide early warning regarding the transformer, and as I said, the digital and innovative techniques which are now increasing the system uh, reliability, that is a way forward in preventive maintenance, will play a crucial role for better stabilization. Thank you for your patient hearing.